embrace the possibilities.
Let's make the future for 360 film.
I think we should do our cities and buildings differently. This is my message. Think.
And development for me means increase in complexity.
It's a simple addition for a designer, but it saves a lot of time in practice.
Why is the resident not so clever?
So this could be interesting for you as well.
Valerio Corniani, my name. I'm going to talk about Wild Oats 11 and one part of Wild Oats 11, the side lifting foil support structure. What is that, basically? It's basically a foil that comes from the side of the boat. Wear your engineering hat, because this is all going to be about composite engineering and carbon fiber, basically. It was an exciting project we did 2 years ago. I'm not allowed to talk what we're doing now, but you probably know, most of you, if you read the news and Sailing Anarchy. And the boat, Wild Oats 11, very successful because of a really strong team, because of an all-round design from Vripack, and because of continuous updates. And this is one of them. What was this update? They found that the boat was nosediving. The boat didn't have the righting moment, was getting old, if you want, needed some upgrade. So they decided to put these lifting foils, which is sliding from port to starboard. And they asked us to work on how to integrate this in the structure. So we did. And this foil basically can only be done, these projects can only be done with a strong team. And this, I'm not going to read all the names, but you can see quite some famous names in there. We are the last one at the bottom. But few people you probably recognize. Paul Beaker, one of them, for example, is quite good on foil design, and of course he was designing the foil and the structures. Because this foil has a bit of load on. I use elephants. I live in Australia. I didn't have enough kangaroos to put there. So an elephant is about 1.5 tons. And this gives you an idea of what the loads is in the structure and what we had to deal with. Fantastic idea. We had some we had a toolbox. We had basically carbon fiber unidirectional laminates. We had strap laminates still made of unidirectional. We had shear plies to dissipate the load out, and we had solid laminate to take the load in abutment. And I'm going to show you here how we used all these tools to dissipate the load. First of all, unidirectional plies, how they work. They work in tension. They don't work well in compression. They work at 0 degrees. If you load them at 90 degrees, no good. So they take the load and bring the load down, basically. Used from chain plates, for example, work really well with that. But when you take the load down, then you have to stop somewhere, and you have to dissipate this load. So you use shear plies, because you want to transfer the load in shear out to the rest of the structure. And when you talk shear, you talk plus or minus 45 in composites. So shear plies are plus or minus 45 fibers, which are taking the load away from these unidirectional plies. And then you also have loads sometimes not only working in tension, but in compression. So you build some C-plates, which are basically made as carbon fiber layers at different angles, and they work well to take the load in abutment, in compression. So these are basically all the tools that we can use as engineers to bring the load somewhere and take the load away. And all these basically were integrated in the case and in the supporting structure of the case. This is the case on the picture, all black because it's carbon, so the 3D shows it better. You have an inner bearing support and you have an outer bearing support. So you basically can take this load and fully fix your case. In the AutoCAD you can see the inner bearing, the outer bearing, and also you can see the pinion drive. Because it's not easy to slide the board from one side to the other when it's loaded. So basically it's an hydraulic pinion that does that. It's quite complicated again, that one to design. And let's focus about the supports. Let's look at the inner bearing support, main load, the vertical load, pushing down when you lift the boat. So gussets, take the load in abutment, and then shear plies to take the load out, dissipate the load out, and unitapes to help dissipating the load on a higher height on the rest of the structure. But then you also have a reverse load and you have a grounding load if you hit something. You don't want to put a big hole in the boat if you hit something. So reverse load, you again butt against the beam, and grounding, you have unitapes in a strap laminate which are taking the load and taking the load away through shear plies in the rest of the structure. Then you have the outer bearing support, main load, the vertical load, is pushing up. So you have gussets, 4 gussets there, which are taking the load in abutment again. And the gussets need 2 beams to stabilize them because you have offset loads. So you need those as well. And in this other slide, you see basically a bit of the gusset, how they're made. They're tapering out because you don't want to bring the load all the way to a point. You want to slowly dissipate this load. So you don't want to be very stiff. So the gusset, you see, they're tapered, and then we have shear plies there again to bring the load out from the gussets, and those 2 beams I mentioned to stabilize everything because you have an offset. Then you have the reverse vertical load. In this case, you're pushing down. So you just use a beam at the bottom. And you need, again, 2 gussets where the supports of the board are. And then the beam basically capping top and bottom, and shear plies transfer the load on the webs around this board. So you think you're sorted, you still have grounding load, and you ground on the trailing edge. So you need a big block on the back and a unit tape in a strap laminate to take the load forward, dissipate the load on shear plies to the top and the bottom, as you can see there. So use all the tools I mentioned before to bring the load and take it around the boat, basically, once we cut a big hole. Last thing, the board. I didn't engineer that, Paul Bicker did. Fantastic. High modulus and intermediate and standard modulus carbon is strong and stiff at the same time. Quite a lot of carbon, as you can see there on that section. So that's basically all for me tonight. I hope you find this interesting. We're doing some more work, as I said, on wild loads. I'm not allowed to talk about that, but it's definitely an exciting project. So thank you again.